In this video, we're going to look at inference for means, and more specifically, we're just going to narrow in and look closer at the large counts condition. So as we do this, let's remind you of what the conditions are for means. Very similar to proportions, except when we get to that large counts or normality condition. So first of all, your sample has to be random, and that's so we can generalize our results to a population. Your 10% condition, it can't be too big, okay? So the sample size must be less than 10% of the whole population, and that's so that sampling without replacement is okay, and that we essentially have independence. Large counts or normality. Well, up until now, we've really only dealt with when we had large populations where they were greater than or equal to 30, but there's really three things that could happen here. So first of all, if your population is normal, the size of your sample doesn't matter, okay? You can assume then that your sampling distribution will also have a normal shape to it. If your population is large, where we use 30 as our cutoff, so if n is greater than or equal to 30 by the central limit theorem, the sampling distribution of your sample mean will also be approximately normal. And then this video is really going to look at, well, what if we have a small sample where it's less than 30? And what we're going to do is we're going to actually then look at a quantitative graph of our sample. And what we're looking for is if it doesn't have strong skewness, or an outlier, it's going to be okay to proceed. All right, so let's just get into this now by looking at a bunch of examples. So what you're being asked to do is our normal or large counts condition, is it met? All right, so first scenario, we want to estimate the average time in minutes to order and receive a regular coffee at a local coffee shop. The times for 5 randomly selected visits to a local coffee shop are shown in the dot plot. So this student chose to make a dot plot of the sample times. First thing I ask myself is, how big's my sample? So it's small, it's less than 5. So I look at my graph and I see what's probably an outlier there close to 6, probably minutes there. So my conclusion is that my condition is not met. The sample size is small, it's less than 30, and the dot plot shows a possible outlier. All right, second one. We want to estimate the average height of high school students. The box plot shows the distribution of height in centimeters for 100 randomly selected students. Okay, so I first consider my sample size. It's large, so you know what? I don't care if I see any outliers because it's large. By the central limit theorem, I'm going to be good. So yes, even though there are outliers, the sample is large, n equals 100 is greater than or equal to 30, so my condition is met. All right, third one here. A middle school counselor wants to estimate how many minutes on average students spend doing homework. A histogram shows the amount of time a random sample of 20 students spent doing homework the previous evening. So I consider my sample size. It's smaller than 30. And so since it is, I'm going to look at the shape of my graph. So this histogram, I don't really see any strong skewness going on or any outliers. I've got some gaps, but I'm going to say, yes, my condition is met. So although the sample size is 20, which is less than or equal to 30, there's no strong skewness or outliers. Okay, so I'm going to give you 3 more. I suggest pause the video and see if you can answer on your own in each case. All right, so 4. Suppose you want to estimate the mean SAT math score of a large high school. Here's a box plot of the SAT math scores for a random sample of 20 students at the school. All right, so n is less than or equal to 30, so I'm going to look at the shape. I see a little bit of skewness there on that right whisker, but I wouldn't say that it's very strong, so I'm going to say, yes, I'm good. So even though my sample's less than or equal to 30, that should say not just less than or equal to 30, let me rephrase that. I'm good how I have it because it's less than 30. The box plot is only moderately skewed to the right, so there are no outliers. All right, 5. How much force does it take to pull wood apart? The stem plot shows the force in pounds required to pull a piece of Douglas fir apart for each of the 20 randomly selected pieces. All right, so here's what I notice. Nice thing about stem plots is they're almost like a histogram if you turn them on their side. So as I look at this, it looks to me like I have got a tail there to the left. So that's some pretty strong skewness. There might even be an outlier. So I'm going to say my condition's not met. The stem plot is strongly skewed to the left with possible outliers. Okay, number 6. To estimate the average GPA of students at your school, you randomly select 50 students. Here's a histogram of their GPAs. So first thing I consider is the sample size. It's big. It's greater than or equal to 30. So despite the shape, or there's nothing really that bad about the shape, I'm pretty good here. So yes, the sample size is large, n equals 50 is greater than or equal to 30, so I am good to proceed. All right, number 7. Now we're going to go through an entire confidence interval here where we do our state, plan, do, and conclude, making sure we have all our components for this confidence interval. All right, so video screen tension. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. And they give us our raw data. So construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. So remember, what's the confidence interval doing? We're trying to estimate and capture the true parameter, which is mu in this scenario, for the mean tension on this day. All right, so let's state what we are doing. So I just quickly typed because I can do that faster than writing. We want to construct a 90% confidence interval to estimate mu, the true mean tension of all the screens produced on a given day. All right, so we're going to go right into our plan. Don't forget here, we want to check our conditions. So if conditions are met, we will construct a 1 sample T interval. Remember, we're doing a T interval because in order to use a Z interval, we would need to know our population standard deviation. And if we don't know the population mean, how would we ever know the population standard deviation? So the normal model is just not good enough here. This is where we go to our T distribution. So just make sure, one of the things you have to do on AP is make sure that you state the name of the test. All right, so let's do our conditions. First of all, random. A random sample of 20 screens was selected. Now we need our 10% condition. So we're doing a little bit of assuming here. We are assuming that 20 screens is less than 10% of all screens produced that day. And then the one we need to look at is our large counts. We only have raw data here, so we need to look at a quantitative graph. So here's my suggestion. It's a time test. You could make a dot plot by hand, but it probably would be easier to make a histogram. So here's what I did. I preloaded my data into L1. I suggest you pause the video and actually do this on your graphing calculator for practice. And I look at my choices for graphs. I'm going to go with a histogram. Another possible option would be a normal probability plot. You could technically do a box plot as well. I just like histograms. So I'm going to do zoom 9. Now, it's not enough just to look at it on the graphing calculator. I'm not really seeing strong skewness. I might have a suspected outlier there, but I'm going to say that it's not really there because it's not too far away. but to really know, I should probably look at my bin size. So if you recall, this is good practice, hit trace and see that this first bin begins at 233.5 and goes all the way to 261.72. Those are ugly numbers to draw on my actual paper. So if I hit window, I can adjust that. So it starts at 233. I'm going to make that 230, nice whole number. And the X scale is my bin size. 28.22 is weird. So nearest like nice whole number would be 30. And now if I hit graph, notice that my shape changed ever so slightly. But now if I hit trace, I see that first bin goes from 230 to 260, and it tells me the frequency of each bar. Now I can easily graph or draw that on my paper. And I'm going to cheat just a little bit here because I can with technology. I just took a screenshot. You obviously won't be able to do that, but this would be really poorly done. I would need to label my X and Y axis and each bin. Okay, and I also need to state what my actual large counts condition is. So I'm stating for my large counts, even though the sample size is small, n equals 20 is less than 30, the histogram of the sample data does not show strong skewness or outliers. And not only have I stated that, I physically drew my histogram. I have it labeled. I should finish labeling my bins there from 230 to 260, and I showed you how to see that on the graphing calculator. So pause and go back if you don't know how to do that, because you will be required to do that on the actual exam. All right, so in order now to show all the steps in the do, I know I'm going to need my sample mean in order to calculate my T star. So easiest way to do that is run your one variable stat. So stat calc, one variable statistics, and I'm using L1, calculate it, and X bar is my sample mean, and S sub X is my sample standard deviation. So from my one variable stat, I know that X bar is equal to 306. Sorry, my pen's not working. 306.32. And my standard deviation, S sub X, is equal to 36.21. And I'm going to get my confidence interval. T star is going to be equal to, well, if I do on the calculator inverse T, I need the area. And if I want a 90% confidence interval, that's going to be 0.05 because it's going to give me the area to the left. So area, and then I need my degrees of freedom, which remember is 1 less than your sample size. So degrees of freedom 19. And on my graphing calculator, I get 1.729. Okay, so my confidence interval is going to be my X bar, which is 306.29, plus or minus my critical value, which is 1.729, times my standard error, which is my standard deviation, 3.621, and I'm using the sample standard deviation, which is why it's called sample error, over the square root of my sample. So I'm going to quickly type that in, and my margin of error, which remember is this whole part right here, is going to be, when I round, I get 14. I actually suggest you typing it in and doing getting these numbers. We might differ ever so slightly by rounding, but you should be very close to me. All right, so here's my confidence interval, which leads me to my conclusion. So I'm going to say kind of this fill in the blank statement here. We are What percent confident? Well, back at the beginning, we said 90% confident that the interval from, and I'm going to say 292.32, and what I need to do here is have a label on it. How is this? It's an average, so 292.2 millivolts to, I didn't give myself enough space here because my pen's not working. I have to write with my finger. Sorry about it being sloppy. To 320.32 millivolts captures the true mean tension, put it in context, in the entire batch of video terminals produced that day. Okay, so I hope you see how to examine the large counts condition in greater detail. One last thing I want to mention to you, which you may have forgotten because we haven't looked at it in a long time, is another type, which would be your probability plot, which is this option all the way over here. So I'm going to select my probability plot to zoom 9, and let's just take a look at what that looks like. Okay, so you could use this instead of your histogram, and what you're looking for is something that's approximately linear. If you remember, we don't get too concerned about little wiggles. I would just draw this. If you hit trace, you can see what these what the actual values are. Let me just remind you. So this X value, 233.5, is the actual data point. What the Y value is your expected Z-score. It's how many distributions it would be away from the mean. So if you see, I've got 3 above, 3 below. So you would need to label your X and Y axis, and you would say, it's approximately linear. Okay, hope that helps. Signing off.